Good morning, everybody. Welcome to a rainy, wintry morning of Chem 1105 with your host, me, Dr. White. Hi, everybody. Hope you all had a good time since the last time we met. I got a lot done, a lot done. But anyways, let's get to work. One of the things one of your colleagues asked me last week, I realized, boy, did I do a good job explaining something? Maybe I didn't. So I'd like to do that. Let's go to Blackboard. And if you see here, this is Blackboard. I'm going to go to student view. So it's like you see it, not like I see it. And on the left here, you'll see different things like announcements, assignments, course information, syllabus, etc. Now, if you click on course information, you'll see right here 3 folders. The first folder, if I click on it, lectures, are all my lecture slides. Any slide I put up, file, is in this file, like chapter 1, and I post it both as a Word document and a PDF file. Now, if you go all the way to the bottom, you'll see that's where the periodic table that we use in this course is, and you can download it. It's a PDF file. Now, if we go back to course information, you'll see there are 2 more folders. One is recommended problem sets, and the other is recommended problem set answers. And if I click on recommended problem sets, you'll see chapter 1 is both a PDF file and a Word document. Now, at the time when I did this, I could only make when I hand wrote something. I hadn't thought of a better way, which I now do. Solve the problem set answers are PDF files. I just wanted to go through that. Now, another important thing, if you look on the left, you'll see assignments. And here's where I'll have the labs. Don't forget, I need as soon as possible the safety contract. I need it so I can make sure I can put down you're actively participating in this class. So if you haven't uploaded this, please do. And if you don't have a scanner, I have instructions how to use a cell phone to make a PDF file. I also have here, if you want, this app, a student, actually a faculty member taught me about this CAM scanner, and it works quite well. I'd highly recommend you use only the free one. Don't pay money for it. You don't need all the bells and whistles. So those are important areas in Blackboard you should be familiar with. If you're not, ask for help. Remember, in my world, in my class, there's no such thing as a dumb question. You can come to lecture and ask questions. You can also, after lecture, ask questions. And finally, I like the special effect, ask questions after lecture, or you can come to my office hours, or you can email me. All right, today's game plan. I'm going to be doing today, going over some of the practice problems for chapter 1. On Wednesday, I'll go through some of the practice problems for appendix A2 and A4. After test number 1, which is coming up soon, you will understand why I call them practice problems. And, ooh, that came out wrong. And think the rain is affecting my voice. All right, let's go through the practice problems. These are things you should know how to answer. Number one, what is one of the 4 branches of chemistry? My favorite is organic, because I'm an organic chemist, but there are 3 others: analytical, physical, inorganic. What is matter? Something that occupies space and has matter. Matter has mass. Sorry. Now, this is very important. What are the 3 states of matter? Solid, liquid, gas. Remember, solid has definite shape, definite volume. Liquid has definite volume, but indefinite shape. And gas has indefinite volume, indefinite shape. Now, name a pure substance you could use in your daily life, and there are many of those, but I put down water, gold, or oxygen. You could have put down nitrogen. Name a mixture you could purchase at your local grocery store. Well, milk is, mouthwash, mustard, and pop. I should tell you, I've spent most of my life, almost all of it, I was born and raised here in the Chicagoland area. And the stuff that comes in cans and bottles, carbonated without alcohol, we call pop, not soda. Now, number 6, is oil, vinaigrette dressing homogeneous or a heterogeneous mixture? Homogeneous, the same throughout. Heterogeneous, 2 separate mixed layers, not the same throughout. And let's do this. If you look on the screen, you see oil, vinaigrette, dressings, bottles. And if you look at the wishbone balsamic vinaigrette, you see 2 separate layers. Which means it's heterogeneous. Is gasoline homogeneous or heterogeneous mixture? Well, if you had a sample of gasoline, let's see if I can find one. And here we have a picture of it. And if you saw it, you'd see it's same throughout. And that means it's homogeneous. Now, you should know the chemical symbols. Give the chemical symbol for a certain element: carbon C, chlorine Cl, O, gold Au, sodium Na, and there are the others you should know. Remember, I've only asked you to learn 37. Now, another aspect of the elements in the periodic table, you should be able to give the name of an element for the following chemical symbol: Na, sodium, Br, bromine. My favorite, C, carbon. Oh, is that near and dear to my heart? Because I'm an organic chemist, and later in the semester, I'll teach you more about organic chemistry. And I have some others. Kr is krypton. In our universe, unless it got stolen to another universe, krypton in our universe is a white colorless gas at room temperature, not a green solid that kills Superman. Now, when we talk about physical and chemical properties, you should know if I give you something, is it a physical or chemical property? And a chemical property indicates how something will change its chemical structure. Physical property is how it changes its state of matter. Water freezes at 0 degrees C. That's a physical property. Ooh, I almost got it wrong. I got number 12 as a repeat. Sorry about that. If we look at 13, iron can rust. That's a chemical property. Gasoline is flammable. Do not test that ever at home or anywhere else. It's a chemical property. Now, give an example of a physical change. Water boiling, ice melting, sodium chloride table salt dissolving in water. Now, give an example of a chemical change. And you could have a candle burning. The wax is undergoing a chemical change. Digesting food. When you eat it, it goes to your stomach. It's undergoing a chemical change. And iron rusting. And that's the problem set for chapter 1. You should know how to answer those questions. And all right, on Wednesday, I'll do Appendix 2A and 2A, A2 and A4. All right, on last Wednesday, we finished chapter 2, but let me go through one more thing again. All right, where did I hide it? Uh-oh. All right, on your screen, let me check. Well, I better change it. Here's the periodic table. And the end of chapter 2, we talked about various families or columns. And the first column, excluding hydrogen, is called the alkali metals: lithium, sodium, potassium. The second column are the alkaline earth metals. Magnesium and calcium are the only ones I've asked you to learn, as are strontium, who Dr. White likes. You'll learn later on why. Going over to the column with the number 7 above it, those are the halogens: fluorine, chlorine, bromine, iodine. And the last column with the number 8 above it are the noble gases. Used to be called inert gases till somebody very creative, a chemist, found a way to make them react. Won the Nobel Prize for that. And example, argon, krypton, neon are noble gases. And on a test, I could ask, give an example of a noble gas or not noble gas with its chemical symbol and name. And you could put down AR, argon, KR, krypton, NE, neon, HE, helium. By the way, helium is the gas they put in balloons you buy for parties. All right, it's time to really get into chemistry. Now we're really getting into it, and it's time for a new chapter. It's new chapter time. Yay! Now we're getting into some good stuff. Yeah. See how happy I am now? You know I'm a chemist, an organic chemist. All right, let's start chapter 3. Chapter 3 starts with the atom. And it's time for me to be subtle. And what is an atom? It's the smallest particle of an element that retains all the characteristics of that element. So if I had atoms of gold, it would have all the characteristics of gold. If I had atoms of sodium, it would have all the characteristics of sodium. Now, a long time ago, a great English chemist, I don't know if they call them, came up with atomic theory. By the way, on this, click, switches off. This won't be on a test, but it's good background information. And the key parts of Dalton's atomic theory, every element is made up of tiny particles called atoms. And atoms of a given element are identical to one another and different from other elements. Now, when you're reading this, you say, oh, duh, that's not that earth-shaking. But at the time, the theories about chemistry were everything from bookie magic to whatever, earth, wind, fire, and water, whatever. But anyways, Dalton came up with these theories, atomic theory, that helped put us on the path we now are on. Now, also, again, switches off, atoms of two or more different elements combine to form compounds. And a particular compound is always made up of the same kind of atoms and number of atoms, which means if you're here in Glen Ellen, water is H2O. If you go to Tokyo, that's one of the few places on this planet I haven't been to, but water is H2O. If you go to Amsterdam, guess what? Water is H2O. If you go to the moon and find water, it's H2O. Now, the other thing that Dalton came up with was a reaction that involved, chemical reaction involves, remember, switches off, the rearrangement, separation, or combination of atoms. Now, this is important. Atoms are never created or destroyed during a chemical reaction. Atoms are never created or destroyed during a chemical reaction. It's just you're rechanging them and recombining them. Hold on, let's see something. Here's from Wikipedia, John Dalton, English chemist. and it talks about when he died and when he lived and all the great things he accomplished. In fact, I believe in England, very big chemical society is called the Dalton Society after him. All right, let's get back to chemistry. Now, click, switches on. When we talk about an atom, there are parts of an atom, and we call those parts of an atom subatomic particles. And what does subatomic mean? Well, how many of you are familiar with a submarine? That's a boat. Sub goes under. That's what sub means. Marine water. Good news. I won't sing one of my favorite songs, We All Live in a Yellow Submarine by the Beatles, because I don't want to ruin your day. No, I'm not going to sing We All. I promised I wouldn't sing it. I like the Beatles, but I love Jimi Hendrix. I was at a concert of his. Never went to Beatles concert. Went to a Beatles movie one time with my best friend, and I think it was Help. And it just opened up. It was a big theater downtown Chicago. And I got in there. We sat down, we looked around. We were the only guys in there. And every time the Beatles were on the screen, the whole theater, every girl started screaming their lungs out. Interesting. Anyways, sub, under, atomic, atom. These are particles, small particles that make up atoms. You should know. Subatomic particles are very small particles that are the building blocks from which atoms are made. These are the particles that make up the atom of every different element. Impressive. Uh-oh, I better be subtle. Hey, know this. What are the subatomic particles? The first one is the electron. And the electron is a subatomic, tongue-tied, subatomic particle that possess a negative charge, electrical charge, which we indicate by this. So the first subatomic particle is an electron, and it has a negative charge. The next one is a proton. And a proton is a subatomic particle with a positive charge, which you should know. And the final one is the neutrons, or the neutrons. And a neutron is a subatomic particle that has no charge at all. Now, if we were face-to-face in a classroom, which last spring I taught this class face-to-face at COD, I would say, all right, everybody together, what's the first subatomic particle? Electron. And I'd ask the class to say that. What's the second? Excuse me. Subatomic particle. That's the proton. Oh, I got something in my throat, a feather. And what's the third subatomic particle? The neutrons. And everybody would say neutrons. And the first time I go through this, it would be pretty quiet. I'd say, all right, come on, fire up. Let's do this again. What's the first subatomic particle? Electrons. What's the second one? Protons. And what's the third one? Neutrons. And you do that, hopefully. Now, you should know electrons have a negative charge. Any proton has a positive charge, and neutrons have no charge. Now, if you're familiar with the TV cartoon program, Jimmy Neutron, they'd ask me, I'd call it Jimmy Electron because they're more exciting than neutrons. But they didn't ask me, so it's Jimmy Neutron. But anyways, you should know electrons, negative charge, protons, positive charge, neutrons, no charge. Every element in the periodic table are made up of these three subatomic particles. The difference is the number of electrons, protons, and neutrons in each element. So, hint, you should know this. Subatomic particle, electrons, protons, neutrons. You should know electrons, negative charge, protons, positive charge, neutrons, no charge. Now, around the 1900s, that's what, about 125 years almost ago, 123 years ago, chemists were investigating what is the atom. It was a mystery. And how did they find out about the atom? They did experiments. And I better be subtle. And know this. Now, when we talk about an atom, there's a nucleus. And that's the center of an atom, which you should know. Now, who investigated the nucleus of an atom? Rutherford, a great chemist at that time. And one of the most famous experiments investigating the atom was Rutherford's gold foil experiment. And what was that? Now, if you look on your screen, let me check to make sure you're seeing what I think you should be seeing. And the answer is yes. Rutherford had a very thin piece of gold foil, and he shot at that. Actually, he did, and I'll explain that in a second. A very high-powered particle, and it was an alpha particle beam. And this is like shooting a cannonball at a piece of tissue paper or Kleenex or Puffs. And you would think it would go boom right through. Well, it didn't. First of all, around the foil, there was called the fluorescent screen, and it would light up to show where those alpha particles are hitting after going through the gold foil. And most of them went straight through, but some of them scattered. Some of them came almost right back. Think about it. You got a cannon and a cannonball, and you're shooting it at some Kleenex or Puffs tissue paper, and one of them, some of them come back. Whoa. Now, as a grad student, which I was when I was at Michigan State, by the way, I'll be forever grateful. I was a graduate student working for Dr. William Roosh at Michigan State. He's now retired. And when you were working on a project he assigned to you, you got unusual results that was not expected. You go and say, Dr. Roosh, this is what I got. What's going on? And he'd say, you know something, do it again. And you would. And you get the same results. And if it was really striking, he'd come out and say, let's do it again. I want to watch. And I can envision a graduate student in Rutherford's lab doing that gold foil experiment once or twice and coming back to Rutherford and saying, Dr. Rutherford, some of the particles came right back. And he said, did you do it again? Yep. And he'd say, I want to watch. And it happened. And what Rutherford was able to elucidate, that's a fancy word meaning figure out, is that the center of an atom, called the nucleus, is very dense. So dense that when these high energy particles hit it, they came back. As you see here. Now, from that and other information, you should know Rutherford was able to elucidate that the center of the atom, which is very dense, called the nucleus, contains only protons and neutrons. The center of an atom, you should know, called the nucleus, center of the atom is called the nucleus, contains only protons and neutrons. The center of an atom, based on his Rutherford's gold foil experiment, is very dense, contains protons and neutrons. Now, the electrons we'll learn later in this chapter are surrounding the nucleus. Now, there's an important series of information concerning atoms of elements. And the first one is the atomic number. Which is on, same thing for Rutherford, and nucleus, which was way on. And you should know this. Atomic number, by definition, is the number of protons in its nucleus. So the number of protons equals what we call the atomic number. Now, this is very important. All atoms have a net zero charge. And because of that, the atomic number equals the number of protons, which has a positive charge. In order for it to have a net zero charge, the atomic number also gives you the number of electrons. So let's say this again. The atomic number, by definition, and I'll never ask you what is the atomic number, but you should know this, and I'll explain why. The atomic number is the number of protons in the nucleus. Remember, the center of the atom. and the atomic number is the number of protons, and therefore, since all atoms have a net zero charge, protons have a plus charge, electrons have a negative charge, the atomic number also equals the number of electrons. Now, if you look at the periodic table on your screen, the number in the upper right-hand corner is the atomic number. Hydrogen H has atomic number of 1. And therefore it has 1 electron, 1 proton. Ooh, one of my favorites, carbon. And carbon, you should know, has the chemical symbol C, and it has what atomic number? 6. And that means it has 6 electrons, 6 protons. The atomic number equals number of electrons and protons. Now, you'll be able to use this periodic table during all the tests in the final, so you don't have to memorize this. Yay. All right, let's look at the following problem. 1 point each, or I could make it also 2 points each, depending on my mood. I can do that. How many protons and electrons are in oxygen? Well, what do? Well, you go to your friendly neighborhood periodic table. I stole that from Spider-Man. But anyways, and where's oxygen? You should know oxygen chemical symbol is O. The number of electrons and protons are equal to the atomic number. Look in the upper right-hand corner, 8. That's the atomic number of oxygen. And because the atomic number of oxygen is 8, oxygen has 8 protons and 8 electrons. Remember, the atomic number equals number of protons and the number of electrons. Let's look at bromine, chemical symbol Br. And we need to go to our friendly neighborhood periodic table. And bromine is a halogen, Br, right over here, the halogens, and it's got an atomic number of 35. Remember, the number in the upper right-hand corner is the atomic number. And the atomic number equals the number of protons by definition. But since all atoms of elements have a net zero charge, it equals the number of electrons. So if the atomic number is 35, bromine has 35 protons, 35 electrons. Next one is lithium. You know something? I better share the fun. So here's your periodic table. I'll give you time now to figure out how many protons and electrons does lithium have. Your turn. Remember, I try and be patient, give everybody time to finish. All right, we look at lithium. What's the chemical of lithium? You should know it's Li. It's an alkali metal. Right here, first column, right under hydrogen. What's its atomic number? 3. And the atomic number equals the number of protons and electrons in that element. So you don't have to write it down, but I will. Lithium, and it has 3 for atomic number, which means it has 3 protons and 3 electrons. And let's do one more because these are fun. Gold. Hopefully by now you've learned it. If not, you should. The chemical symbol for gold is Au. Let me write that larger. Au. And I'll give you a chance to have some more fun. How many protons and electrons are in gold? Your turn. All right, let's do it. The question is, how many protons and electrons does gold have? So you have to find gold on the periodic table. Chemical symbol is Au. That's right here. And it has atomic number of 79. And 79 equals number of protons equals the number of electrons. So gold has atomic number of 79, and that means it has 79 protons and 79 electrons. And this is something, skill you should have for test one, and also the rest of the semester, you'll need it. Now, let's review. The atomic number equals the number of protons in its nucleus. Since all atoms have a net zero charge, that equals the number of electrons. And just a quick real review. Remember the subatomic particles, the particles that make up an atom of an element, are the electrons, protons, and neutrons. Now, every electron, you should know, has a negative charge. Every proton has a positive charge, and every neutron has no charge. And the nucleus of an atom, which is the center of an atom, contains only protons and neutrons, and it's very dense, and that we learned from Rutherford's gold foil experiments. Now, an important concept about atoms are the atomic mass number. And by definition, that's the sum of the protons and neutrons in a nucleus. And I'll never ask you what's the atomic mass number of an atom. But this is important background information. If I look at the clock, it's time for a break. I'll see you in about 5 minutes. I'm going to get up and stretch, and we'll continue then. let's get going. I was just looking out of my weather window, my backyard, and guess what? It's still raining. We had enough rain. All right, before I move on, quick reminder from the management, me. Remember, the safety lab we did last week, Tuesday, is due tomorrow in the upload to assignment area Blackboard. Remember, the assignment safety lab we did last week is due tomorrow. You don't need the lab kit. I know some of you, for various reasons, financial, like waiting for your scholarship, have not got your kit yet. If you don't buy tomorrow's lab we're doing, I'll give you extension, but you still need to purchase it. And when you do the actual labs, the first lab safety, you don't need to do a selfie. But as for my syllabus and departmental regulations, you need to have a selfie with one of the chemicals or equipment you're using for that lab. And you need to upload it when you upload to the assignment area, that lab. If you don't, you get zero points. But the first lab, you don't have to. Don't forget, I think 2 or 3 of you have not uploaded your safety contract. I need it today or tomorrow. I'll send out an email to those who haven't. All right. We're talking about the atomic mass number, which is the sum of protons, the number of protons, and number of neutrons in the nucleus. Nucleus, center of the atom. Now, it turns out we have what's known as isotopes, and this affects what we call the atomic mass. Now, I'll never ask on a test, but you should be at least familiar. Isotopes are atoms that have the same number of electrons and protons, but isotopes have different number of neutrons. So isotopes of an atom, of an element, have the same number of electrons and protons, get them from the atomic number, but have the same number of neutrons. Now, you see on your screen right now, I pulled up the different isotopes of uranium. And the most famous is uranium-238. But these N-233 is from the atomic bomb. And this, the only difference between all these isotopes is the number of neutrons. Now, what is the reason I'm talking about this? Good question. Thank you. Oh, before switch is totally off, there's something called the nuclear symbol. I've never used it. I've never put it on a test or a final, but it's the chemical symbol, and the upper corner left is the atomic number, and in the lower left is the the upper corner. Say I got it wrong. Let's back up. Norp. All right, nuclear symbol, something I've never used, and it won't be on my test or final. But A is the atomic mass number, Z is atomic number. Now, switch is off and it's part of the way, but you'll understand there's a very, very important concept in chemistry called the atomic mass. And your instructor will call it the atomic weight. And since we're not going to leave the planet, I can get away with that. Now, what is the atomic mass? It's the weighted average mass of all naturally occurring isotopes of an element based on the abundance of that element and mass of each element. So if you had carbon, and this is not correct in real life, 80% isotope C12 and 20% C14, the atomic mass, which I will call atomic weight, is 80% 12 plus 20% 14. 0.8 times 12 plus 0.2 plus 4 times 14. And you get a number. Now, in real life, and we call that the atomic mass, or I'll call it the atomic weight. Now, where can you find this? Well, your friendly neighborhood periodic table. And if you look at the atomic periodic table, and you look underneath the chemical symbol, you'll see a number. Hydrogen, 1.008. Carbon, 12.011. Oxygen, 15.999. That's the atomic weight or atomic mass. This is something you should know how to find. And so it's time for a special gift from Dr. White. Don't tell anybody I'm being nice. Shh. But my special gift in my course, we will use all atomic weights, the 3 significant figures. In my course, we'll use all atomic weights, the 3 significant figures. And by the way, when I was in the chemical industry, I did the same. And I did calculations. Some of them were hundreds of thousands of dollars, riding on, did I use do the calculations right? And I had to use the atomic weights of elements. So if we look at what's the atomic weight of oxygen to 3 significant figures. Oh, oxygen, number underneath it, 15.999 is the atomic weight. And how do we round 15.999 to 3 significant figures? Keep the 1, keep the 5, keep the 9. Those are 3 significant figures. Use this number to round off. Is that 4 or less, or 5 or more? And time's up, 5 or more, drop this, increase that by 1. Now, 0.9 when you increase it by 1, becomes 1.0. And 1.0 plus 15 equals 15.0. That 16.0. Let's try that again. 1.0 plus 15, bad, Dr. White, is 16.0. So the three significant figures, this becomes 16.0, which is what you'll use. They'll make your life a lot easier, trust me, which is a good thing. So what time is it? It's you practice using the periodic table. You should know how to locate an element, determine its atomic number, determine the number of electrons and protons, and determine the atomic mass of an element. And let's do some. Given the name of an element, you should know, be able from the periodic table, figure out the atomic number and the atomic mass, the three significant figures. Remember, the atomic number equals number of electrons and protons in that element. So how do we do sodium? You should know the chemical symbol for sodium, Na. And now we go to our periodic table. And if we look at the upper, here's Na, alkali metal. If we look in the upper right-hand corner, that's the atomic number. Now, underneath, you have the atomic weight, 22.989. However, you have to round it off to three significant figures. So we keep the 2, keep the 2, keep the 0.9, use the next number, 3/6. The fourth one I used to round off. Is that 4 or less or 5 or higher? And 5 or higher. I'll drop that, increase that by 0.1 or 1 unit, and that takes us to 23.0. And that would be the correct answer. And here's one for you to try. What's the atomic number? What's the atomic mass of calcium? Don't forget atomic mass, round off the three significant figures. Your turn. Remember, you're trying to find out what's the atomic number and the atomic mass, the three significant figures of calcium. And giving everybody time to finish. All right. Calcium, you should know, has the chemical symbol of Ca. It's an alkaline earth metal right here. Atomic number is 20. Underneath, atomic mass 40.078. 40.078. Atomic number is this. But you have to round that off to three significant figures. Why don't you try it and I'll do it. All right, let's do it. Get three significant figures. Keep the 4, keep the 0, keep the 0. Remember, zeros at the end with a decimal point are significant. The 7 round off is that 4 or less, 5 or higher, and 5 or higher. Drop that, increase that by 1, which would mean 40.1, and that's the atomic mass of calcium. And later on, we'll talk later on about what actual calcium helps make strong bones. Oh, let's do one more. Find the atomic number and the atomic mass, the 3, 6. I gave it away. Sometimes I think of, let's still do it. What's the atomic number and atomic mass? The three significant figures, silver. I already gave it away. Chemical symbol Ag. And it's your turn. All right, let's take a look. Where's silver? It's below copper, Ag. What's the atomic number? Remember, that's equal number of protons and electrons. Upper right-hand corner, 47. Now, the atomic mass or weight underneath 107.868. So, atomic number 47. Here's the atomic weight. But atomic number 47, atomic weight, but for my class, you have to round off all atomic masses or weights to 3 significant figures. I'll let you do that. My turn. I'll do it. Go. Yes, sir. Your turn. All right, let's do this. How do you round 107.868 to 3 significant figures? Keep the 1, keep the 0. Remember, combined zeros are significant. Keep the 7. Use the 8 to round off. Is that 4 or less or 5 or higher? Time's up. It's 5 or higher. I drop all that, increase that by 1, and the answer is the atomic weight or mass of silver, the 3 significant figures, is 108. Now, time for a personal story. I happened to be one day years ago pulling up at a stoplight, and the car in front of me had this license plate, HIHOAG. I looked at it. In about 30 seconds or less, I started smiling and laughing. That is wicked. And what is this? Hi, ho, AG, silver. And that's the way the Lone Ranger's TV show and movies started. And when I was a boy, now I'm feeling really good. It was a great memory. The most popular TV show on TV for children, boys, was The Lone Ranger. And it always started out, hi ho silver. And go to YouTube. You can see that. I think everything's on YouTube except my high school graduation. Everything else is there. I got my bachelor's degree, my PhD. I don't know, but when the Johnny Depp movie came out, I saw the trailer. What a disgrace to the legend of the Lone Ranger. I didn't even go see it. Tano with a dead bird on his head? No. Tano was a great character played by Jay Silverheels in the TV program. He was the Lone Ranger's sidekick. Anyways, now I brought back a good memory. Now, we've talked about electrons, neutrons, and protons. And in the nucleus, the center of an atom, That's where the protons and neutrons are. Where are the electrons? Well, let's talk about that. Now, the next couple of slides, click, I'm turning the switch. Will this be on the test? Off. Now, when we talk about electronic structures, where are the electrons? I need to talk about electromagnetic radiation. And that's energy that travels as waves, just like waves on an ocean or Lake Michigan, through space. And waves have wavelengths, how far they are apart, and how frequently they come in really quick. And this is found in the electromagnetic spectrum. And this arrangement of all various forms, where switch is off right now, of electromagnetic energy in order of decreasing energy. Now, if you look on your screen right now, you'll see on the right-hand side, it has gamma scientific. And underneath the visible spectra, you see the electromagnetic radiation spectrum, electromagnetic spectrum. And it goes from gamma rays to radio waves, such as radar, TV, FM, AM. Now, on the left are the most energetic, gamma rays, then X-rays, UV. Now, in the middle, they have a little slice which they expand on top, is the visible spectrum. In other words, light. And white light you see exists as a combination of these colored lights. I don't know if you remember from high school, I learned, and I don't know if you remember, Roy G. Biv, going from red, orange, yellow, Roy G. green, Biv, blue, or violet and blue. And here's the visible spectrum. Now, it turns out electromagnetic spectra plays a role in helping understand where are the electrons. Really? Yep. Now, it turned out scientists, chemists really found what they call the atomic spectra. What is that? The atomic spectra is when light is emitted from heated elements, it is passed through a prism. And on your screen right now, if you had, say, an element like hydrogen, and you put a energy through it, put it through a slit, put it through a prism, you'd see on a black surface these lines. And some of them are very hard to see, like a 410.1, 434.1, 486 is a little darker, and the red one is 656.3. And whenever you were to heat up hydrogen, that atomic spectra was what you would see. You take iron right here. Wow, there are a lot of lines right here. And helium, there's only really a couple that are very faint. And if you were to heat up sodium, you see slight green and these yellow colors. Mercury has these. And these are ways of identifying elements, which, if you ever watch the CSI program, they've taken atomic spectra of the sample, and that helps identify what elements are in that sample. So we have these atomic spectra. When you heat up an element, it gives off light at characteristic frequencies, these colors. So what does that mean? Good question. The light given off corresponds, again, switches to off click, to electronic energy levels of the electrons. And these associational lines in the atomic spectra with changes are associated with changes in the energy of the electrons. Now, it turns out, because you see certain lines for certain elements, these energy levels are assigned what we call principal quantum numbers n. They're also called shells. And this helps us determine where are the electrons. And again, this slide switches off. Click, it won't be on a test. Time to be subtle again. Hint, know this. Let's talk about electron arrangements within atoms of elements. In other words, where are the electrons? Because the protons and neutrons are in the center of the nucleus. Now, electrons are found around the nucleus in what we call the electron shells. An electron shell, and I'll never ask this you should know this, is the region of space about the nucleus that contains electrons that have approximately the same energy and spend their time approximately the same distance from the center, the nucleus. So electron shell has electrons in a region of space about the nucleus that contain electrons that have approximately the same energy and spend their time, most of their time, approximately the same distance from the nucleus. Now, each electron shell is made up of electron subshells. And an electron subshell is the region of space within an electron shell that contains electrons that have the same energy. So each shell has a subshell or more than one subshell. Settle time again. Now, electron shells have very difficult names, and they are shell 1, shell 2, shell 3, and shell 4. That's what we'll cover in this class. Now, the first shell is called shell 1. The second shell is shell 2. The third is shell 3. And the fourth is shell 4. Now, shell 1 only has one subshell. Shell 1 only has one subshell. I got to work on my arrows. Shell 2, this is hard, has two subshells. Shell 2 has two subshells. Shell 3, ooh, this is real hard, has three subshells, and shell 4 has four subshells. Now, the top shell 1 is the lowest energy shell. And this you should know. And as you go down, you increase the energy of the shells. On this table, shell 4 is the highest energy shell. Again, shell 1 is the lowest energy. As you go down the table, the energy of the shells increase, and shell 4 has the highest energy. Now, one of the things I came up with a couple of years ago when I was challenged in a good way by another faculty member at COD who taught general chemistry like this, also 1211, and that is when I give a test, am I testing your knowledge of chemistry, or am I testing your knowledge of chemistry and your memory? What am I testing? Your knowledge of chemistry or your knowledge of chemistry with your memory? Hope I don't put a hole in my awful humor time, sorry. But anyways, I finally realized I should just be testing your knowledge of chemistry, not your knowledge of chemistry and your memory. So what did I do? In the past, students would have to memorize this table for test number 1 and the final 2. And I changed that. Now we go back to Blackboard, go to course information, go to lectures, and scroll way, way down. You'll see important information, test number 1. And I have this as both a Word document and a PDF file. And I give this to you so you will know. Let's open one up. All right, where did I hide it? Here it is. And if you look on your screen, you'll now see important information, test number 1. At the end of test number 1, you will be given this information. I have the formulas for temperature conversion, and notice electron shell, shell 1, 1 subshell, shell 2, 2 subshells, shell 3, 3 subshells, shell 4, 4 subshells. In the past, you'd have to memorize all this. And there's still some memorization, but I've cut way down. which I think is a good thing. So you should know electron shells, shell 1, shell 2, shell 3, shell 4. You should know from this table, shell 1 has 1 subshell, shell 2 has 2, 3 has 3, 4 has 4. Now, you should also know, and I didn't put this on the table, there's still a little memorization you have to do, that shell 1 is the lowest energy of the shells. And when you move down this table to shell 4, on this table, that's the highest energy shell. Now, let's talk about the subshells. Remember, the shells are the region in space about a nucleus, center of an atom, that contain electrons approximately the same energy and spend their time, most of their time, approximately the same distance from the nucleus. Now, electron shells have electron subshells. And that's the region of space within the electron shell that contains electrons that have the same energy, which means shell 1 has only 1 subshell with electrons the same energy and distance from the nucleus. Shell 2 has 2 subshells where you have your electrons in shell 2. Now, subshells are designated by letters S, P, D, and F. Now, S is the lowest energy, and when you go this way, F is the highest energy. Another way of saying that is this symbol, which you see here, means less than. So the energy of S is less than P, the energy of P is less than D, and the energy of D is less than F. Now, never ask on a test or a quiz, but a while back, students asked, what is that S, P, D, and F? When they're doing the atomic spectra, they named the line from the S subshell sharp. Don't ask me why. I don't know. This is not my area of expertise in chemistry. And P, another line, was called principal, D diffuse, F fundamental. Now, again, these are the various subshells. Now, settle time. Know this. So I have a capital, really should be lowercase. Don't worry about it. I don't. Now, the first subshell is S, and that contains a maximum I should have put this in here, maximum number of electrons, 2. P, maximum number of electrons, 6. D, maximum number of electrons, 10. And F, maximum number of electrons, 14. Now, you should know that when you go from the top to the bottom of the table here for subshells, S is the lowest energy, F is the highest. As you go down, the energy of that subshell increases. If you look at important information, test number 1, I give you the subshells and the maximum number of electrons in a table before students have to memorize this. Uh-oh. I just looked at the clock. We're just about out of time. Time flies when you're having fun with electrons, protons, and neutrons, and shells and subshells, electronic shells and subshells with Dr. White. Let me remind you, tomorrow, the safety lab we did last Tuesday is due, and you need to upload it to Blackboard. If you have any questions, feel free to email me or come to my office hour or ask after class. Next, don't forget, I need, and there are about 2 or 3 people who haven't done it, I need your distance learning safety contract to be signed, dated, and uploaded to Blackboard by tomorrow. I need it. So please help me out. And with that, I'm done for today. And that means it's time for me to say, Gang gesund, goodbye. I'll do that again. Gang gesund, goodbye. That sounds better.